हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी हाइजेंस प्रिंसिपल और यंग्स डबल स्लिट एक्सपेरिमेंट जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम इंटरफेरेंस और डिफ्रैक्शन के पैटर्न्स देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम वेव ऑप्टिक्स के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात। हमारे चैनल पर 97% लॉग वीडियोस देखते हैं, लेकिन सब्सक्राइब नहीं करते। और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Kamal and Deep are traveling in the train. Then, a train passes from the nearby track.
The train's whistle is so loud.
Yeah, it's really not tolerable.
I wanna ask you something.
Yes, Kamal, sure.
When the train passes us, the sound is loud, and when it moves away, the sound dies. Can you please explain me about this?
Okay, Kamal, I will tell you. This is due to the Doppler effect. The train producing sound waves was moving with respect to us. It causes an apparent shift in the frequency of sound waves for us. That's why sound rises when the train comes near us and dies when train goes away from us.
It's really interesting. I wanna know something more about this.
Students, today we will study about the wave optics. Objectives. At the end of this lesson, you will be able to define wave front, know Huygens principle, understand refraction and reflection of plane waves, describe plane wave front in lens and prism, understand the Doppler effect, define electromagnetic waves, understand coherent and incoherent addition of waves, describe interference of light waves, explain Young's double slit experiment, explain conditions for sustained interference. Wave front. Wave front is defined as the locus of all the particles of a medium vibrating in the same phase at a given instant. A line perpendicular to a wave front is called a ray. The phase difference between any 2 points situated on the same wave front is zero. The shape of a wave front depends upon the shape of the source of disturbance. The distance from one crest to the next crest is equal to wavelength lambda. The phase difference between any 2 points in the same phase on two consecutive wave fronts is 2 pi. So, at any given crest and trough, the phase is 2n pi and 2n plus 1 pi respectively, where n is an integer. Types of wave fronts. There are different types of wave fronts which are given as spherical wave front. The wave front of light waves radiated by a point source may be represented by spherical surfaces concentric with the source. Plane wave front. At large distances from a point source, the spherical wave fronts are of very large radii and small portions of these can be considered planes. Cylindrical wave front. A line source can produce a cylindrical wave front coaxial with the source. Huygens principle. Huygens principle is a geometrical construction for finding the shape of a new wavefront at some instant. According to this principle, every point of a wavefront is a source of spherical secondary waves called wavelets, which spread out in all directions with the speed of propagation of the wave in that medium. The new wavefront at a later instant is the surface tangent to the secondary wavelets called the envelope of the secondary wavelets. Laws of reflection at a plane surface. The angle of incidence is the angle between the incident ray and the normal, but the ray is perpendicular to the wavefront and the normal perpendicular to the surface. Hence, the angle of incidence is the angle between the incident wavefront AB and the surface PQ. Similarly, the angle of reflection is the angle between the reflected wavefront CD and the surface PQ. Now, from the geometry of triangles BAC and DAC, AD is equal to BC and AD is equal to AC. We can say that these are congruent triangles. Hence, the angle of incidence is equal to the angle of reflection. Also, the incident ray, the reflected ray, and the normal are all in the same plane. Hence, the wave theory has proved the laws of reflection at a plane surface. Reflection of plane waves. Consider a parallel beam of light incident on a plane surface separating two media. The planes AB, A1-B1 and A2-B2 are the positions of the incident wavefront at different instants. A Huygens wavelet originating from point B in the wavefront AB will move a distance B' in the second medium in the same time that the wavelet from A expands in the first medium to include point A' on the surface XY. Since the two wavelets have radii A' and B' are not in the same medium, they move with different speeds, say V1 and V2 respectively. Case 1. If medium 2 is optically denser than medium 1, then V1 is greater than V2 and hence A' is greater than B'. The ray is bent towards the normal. Case 2. If medium 2 is optically rarer than medium 1, then V1 is less than V2 and hence A' is less than B'. The ray is bent away from the normal. Distance A' is equal to V1 is equal to lambda 1, the wavelength of light wave in medium 1. Distance B' is equal to V2 is equal to lambda 2, the wavelength of light wave in medium 2. Therefore, V1 by V2 is equal to lambda 1 by lambda 2, or it can be written as V1 by lambda 1 is equal to V2 by lambda 2 is equal to nu. The above expression shows that the frequency of the light wave remains unchanged during refraction. The wavelength decreases when the light wave refracts into a denser medium and the wavelength increases when the light wave refracts into a denser medium. Plane wavefront in lens. Consider a plane wavefront ACB incident on a double convex lens. According to Huygens hypothesis, each point of the wavefront acts as a source of secondary waves. These secondary waves will travel through different thickness of the lens. The time taken by the secondary wave to travel through CP1 in air plus P1, P2 in lengths will be the same as the time taken by waves to travel through AX plus XD in air. So, all the secondary waves from the incident plane wavefront ACB reach dP2E at the same time. Thus, dP2E is the refracted wavefront. This wavefront is converging in nature. Plane wavefront in prism. Consider a plane wavefront BD incident on the prism. According to Huygens' hypothesis, each point of the wavefront acts as a source of secondary waves. These secondary waves will travel through different thicknesses of the prism. The time taken by a secondary wave to travel through distance BC in the material of the prism is the same as the time taken by a secondary wave to travel through a distance dA plus AE in air. The distance travelled in air is clearly greater than the distance travelled in prism. This is because the velocity of secondary wave in the material of the prism is less than that in air. All the secondary waves starting from BD reach CE at the same time. So, CE is the emergent wavefront. The Doppler effect. Consider when there is a medium and the source moves away from the observer, then latter wavefronts have to travel a greater distance to reach the observer. The time taken between the arrivals of two successive wavefronts is hence longer at the observer than is at the source. Thus, the frequency as measured by the source will be smaller. This is known as the Doppler effect. The Doppler effect is observed whenever the source of waves is moving with respect to an observer. The Doppler effect can be described as the effect produced by a moving source of waves in which there is an apparent shift in frequency for observer. Redshift and blue shift. Redshift. The increase in wavelength due to Doppler effect is known as redshift because the wavelength in the middle of the visible region of the spectrum moves towards the red end of the spectrum. Blue shift. When waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. The Doppler shift is given by delta nu by nu is equal to minus v radial by c, where v radial is the component of the velocity along the line joining the source and observer. Electromagnetic waves. A wave of energy consisting of electric and magnetic fields is known as electromagnetic wave. Variations in both electric and magnetic fields occur simultaneously. As a result, they attain their maxima and minima at the same place at the same time. The directions of electric and magnetic fields are mutually perpendicular as well as to the direction of propagation of the wave. Thus, these waves are transverse in nature. The velocity of the waves depends entirely on the electric and magnetic properties of the medium in which these waves travel. Superposition of waves. Principle of superposition states that when two or more than two waves travel in the same medium at the same time superimposing each other, then the displacement of the resultant wave at any instant is equal to the vector sum of the individual displacements at that instant. Let vector y1, y2, y3 and so on be the displacement vectors due to the individual waves at any instant acting separately, then according to the principle of superposition, the displacement of the resultant wave at that instant is given by vector y1 plus y2 plus y3 plus so on. Coherent and incoherent sources of waves. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency, and in same phase or having constant phase difference. There are two general methods for producing coherent sources are follows. By division of wavefront. In this method, the wavefront is divided into two or more parts by use of mirrors, lenses, or prisms. By division of amplitude. In this method, the amplitude of incoming beam is divided into two or more parts by partial reflection or refraction. These divided parts travel different paths and are finally brought together to produce interference. Incoherent sources emit light with frequent and random changes of phase between the photons. Tungsten filament lamps and ordinary fluorescent tubes emit incoherent light. Interference of light waves. Interference of light is the phenomena of redistribution of light energy in the medium due to superimposition of light waves coming from two coherent sources. There are two types of interferences. They are constructive interference, destructive interference. The interference is constructive at the points where the resultant intensity of light is maximum, and the interference is destructive at the points where the resultant intensity of light is minimum. Constructive and destructive interference. Constructive interference. At the points of the medium where the resultant intensity of light is maximum, the interference is called as constructive interference. For constructive interference, phi is equal to 2n pi or p is equal to n lambda, where n is equal to 0, 1, 2, 3 and so on. Phi is equal to phase difference. P is equal to path difference. Lambda is equal to wavelength of light. Destructive interference. At the points of the medium where the resultant intensity of light is minimum, the interference is called as destructive interference. For destructive interference, phi is equal to 2n plus 1 pi or p is equal to 2n plus 1 lambda by 2. Young's double slit experiment. In Young's experiment, monochromatic light from a source passes through a narrow slit S and falls on two closely spaced narrow slits S1 and S2 placed at some distance from S. The slits S1 and S2 act as coherent sources of light waves because the light from each is derived from the same primary source S. These waves interfere constructively and destructively at different points on the screen to produce a pattern of alternating bright and dark bands called interference fringes on the screen. Mathematical analysis in Young's double slit experiment. Let S1 and S2 be coherent sources at separation D and capital D be the distance of screen from sources, then path difference between waves reaching at P is given by product of Yn and D divided by capital D. For maxima delta is equal to n lambda, position of nth maxima is given by n capital D lambda upon small d. Position of nth minima is given by n minus 1 upon 2 into capital D lambda upon small d. Fringe width. Fringe width is defined as the separation between two consecutive maxima or minima. Beta is equal to y into n plus 1 minus yn, which is equal to capital D lambda upon small d. Angular fringe width is given by beta upon d, which is equal to lambda upon d. Use of white light. When white light is used to illuminate the slit, we obtain an interference pattern consisting of a central white fringe having on both sides symmetrically a few colored fringes and then uniform illumination. Example. Let's take an example on Young's double slit experiment. The two slits in Young's experiment are 3 mm apart, illuminated by a light of wavelength 480 nanometer. The screen is at 2 meters from the plane of the slit. Find the separation between 8th bright and 3rd dark fringe with respect to central bright fringe. Let's see the solution. Distance of 8th bright fringe from center is given by 8 capital D lambda upon small d. Distance of 3rd bright fringe from center is given by 5 capital D lambda upon 2 small d. We have y is equal to y8 minus y3. By putting the values and calculating, we get y is equal to 11 capital D lambda upon small d. Putting the values in the above equation and calculating, we get value of y is equal to 3.52 millimeter. Hence, the separation between 8th bright and 3rd dark fringe with respect to central bright fringe is 3.52 millimeter. Conditions for sustained interference. The following conditions are necessary to obtain a continuous or permanent interference. The light should be monochromatic. If this is not so, the fringes of different colors will overlap. The two sources producing interference must be coherent. The wave trains causing the interference must have light waves of the same wavelength and same velocity. The two interfering wave trains must have the same plane of polarization. To observe interference fringes clearly, it is necessary that the fringe width is sufficiently large. Did you know? For manufacturing reasons, a perfect lens has a spherical surface shape, though theoretically the ideal surface should be aspherical. Light slows down, bends towards the normal, and has a shorter wavelength when it enters a higher refractive index or as it moves to denser medium. Reflection of waves of sea walls or other barriers can cause an interference pattern called a standing wave. In standing waves, crests do not move laterally. Summary. Let us summarize what we have learned. Wavefront is defined as the locus of all the particles of a medium vibrating in the same phase at a given instant. Every point of a wavefront is a source of spherical secondary waves called wavelets. The wavelength decreases when the light wave refracts into a denser medium. The Doppler effect is defined as the effect produced by a moving source of waves in which there is an apparent shift in frequency for observer. When waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. A wave of energy consisting of electric and magnetic fields is known as electromagnetic wave. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency, and in same phase or having constant phase difference. Interference of light is the phenomena of redistribution of light energy in the medium due to superposition of light waves coming from two coherent sources. Introduction. Tanuj, what are you doing? I'm searching one of the science educational DVD. Can you please help me in finding the DVD? Sure. Amit, can you please tell me something? Yeah, definitely. Why is this DVD shining in a rainbow pattern? What's the reason behind this colorful shine? Okay, I will tell you. It happens due to the diffraction of waves. Diffraction occurs when the wavelength of the wave are in order of the object size. The closely spaced tracks on the DVD are comparable with the wavelength of wave. That's why we observe the colorful shine of DVD. Okay, I got it. It's quite an interesting fact. Can you please tell me something more about this? I'm curious to know. Okay, let's today study more about the wave optics. Objectives. At the end of this lesson, you will be able to define diffraction, understand diffraction due to a single slit, differentiate between interference and diffraction, define resolving power, calculate resolving power of a microscope and telescope, define polarization and Polaroids, understand Malu's law, describe polarization by scattering, reflection and refraction. Diffraction. Diffraction of light is the phenomena of bending of light waves around the edges of an obstacle or an aperture of size comparable to the wavelength of the incident light waves. Diffraction is of two types: Fresnel's diffraction and Fraunhofer's diffraction. In Fresnel's diffraction, source and screen are close to the obstacle and light after diffraction appears converging towards the screen and hence no lens is required to observe it. In Fraunhofer's class, source and screen are at large distance from the obstacle. A converging lens is used to observe it. Diffraction due to a single slit. Consider a plane wavefront incident on the slit AB. Each point of the incident wavefront will be a source of secondary wavelets. These wavelets emanate from the wavefront in the same phase. To understand the formation of central maximum, the slit can be imagined to be divided into a number of very narrow strips of equal width parallel to the slit. All the wavelets originate from the narrow strip in the same phase. All these wavelets arrive at O in the same phase. These wavelets reinforce each other's effect to give maximum intensity at O. Now consider the formation of secondary minima and secondary maxima. Secondary wavelets diffracted at angle theta reaching a general point P on the screen. The wavelets shall not arrive at P in the same phase because these cover unequal distances in reaching P. Path difference between the extreme wavelets is given by Bn is equal to d sin theta. The condition for first secondary maximum is given at angle equals to 3 lambda upon 2d. The condition for second secondary maximum is given at an angle equals to 5 lambda upon 2d. Hence, the condition for nth maximum is given at an angle equals to 2n plus 1 lambda upon 2d. Width of secondary maximum is given by beta is equal to d lambda upon small d. Width of central maximum is given by beta naught is equal to 2d lambda upon small d. A distinct diffraction pattern is possible only if the slit is narrow. If the slit is made sufficiently large, then the secondary maxima will not be visible. Example. Let's take an example on diffraction pattern due to single slit. Determine the angular spread between central maximum and first order maximum of the diffraction pattern due to a single slit of width 0.25 mm when light of wavelength 5890 Armstrong is incident on it normally. Let's see the solution. We know that half the angular spread is given by a sin theta is equal to 2n plus 1 lambda by 2. On equating this, we get lambda by 2 is equal to 3 lambda by 2. When theta is small, then value of sin theta is equivalent to theta. It gives a theta is equal to 3 lambda by 2. On putting the values, we get the value of theta is equal to 3.530 multiplied by 10 raised to the power minus 3. Hence, the total angular spread is equal to 3.530 multiplied by 10 raised to the power minus 3 radians. Difference between interference and diffraction. Interference is the result of superposition of waves starting from two different wavefronts, whereas diffraction is the result of superposition of waves starting from different portions of the same wavefront. All bright fringes in an interference pattern are of same intensity, whereas intensity of brightness in a diffraction pattern decreases as one moves away from the central bright fringe. The points of minimum intensity in an interference pattern are perfectly dark, whereas the points of minimum intensity are not perfectly dark in a diffraction pattern. Resolving power. The ability of an optical instrument to produce separate images of two objects very close together is called resolving power. Rayleigh criteria. When the central maximum in the diffraction pattern of one point source falls over the first minimum in the diffraction pattern of the other point source, then the 2 point sources are said to have been resolved by the optical instrument. Resolving power of a lens. The resolving power of a lens is its ability to resolve 2 points that are close to each other. The resolving power is directly proportional to the aperture of the lens and inversely proportional to the wavelength of light used. Resolving power of a microscope. The resolving power of a microscope is defined as the reciprocal of the distance between two objects which can be just resolved when seen through the microscope. 1 upon delta D is equal to 2 mu sin theta upon lambda, where lambda is the wavelength of light, mu is the refractive index of the medium, and theta is the half angle of the cone of light from the point object. The term mu sin theta is called the numerical aperture of the objective. To increase the resolving power of a microscope, mu is increased by using suitable oil between the object and the objective. Resolving power of a telescope. Point-like sources separated by an angle smaller than the angular resolution cannot be resolved. A single optical telescope may have an angular resolution less than 1 arc second. The angular resolution of a telescope is given by R is equal to lambda divided by D, where lambda is the wavelength of the observed radiation and D is the diameter of the telescope's objective. Resulting R is in radians. Sources larger than the angular resolution are called extended sources and smaller sources are called point sources. The resolving power of a telescope is the reciprocal of the smallest angular separation between two distant objects whose images are separated in the telescope. d theta is equal to 1.22 lambda divided by A. A telescope with a larger aperture objective gives a high resolving power. Polarization. Polarization of light is the phenomena of restricting the vibrations of light in a particular plane. Plane polarized light is the light in which the vibrations of light are confined in a particular plane. Plane of vibration is the plane which is perpendicular to the plane of vibration. Polarizing angle is that angle of incidence at which the reflected light is completely plane polarized. Polaroids. Polaroid is a type of plastic sheet that can polarize a transmitted beam of normal light because it is composed of long parallel molecules. It only transmits plane polarized light if these molecules are parallel to the plane of polarization. Since reflected light is partly polarized, it is often used in sunglasses to eliminate glare. Linearly polarized light can be produced from unpolarized light with the help of Polaroid. The direction of polarization that a polarizing material allows through is called the transmission axis. Uses of Polaroids. Some important uses of Polaroids are following. It is used to avoid the glare of light. If we use sunglasses fitted with Polaroid, the eyes will not experience any glare. Polaroid sheets are fitted in car headlights and windscreen to avoid glare. Two Polaroid sheets are put one behind the other to control the light in window of aeroplane and big hotels. Camera used to photograph the clouds is fitted with Polaroid before the camera lens. Properly designed Polaroid glasses are used to produce and view a three-dimensional image. They are also used for studying optical properties of metals.
Malus's law. According to Malus's law, when completely plane polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axes of the analyzer and the polarizer. Suppose that theta is the angle between the transmission directions of the polarizer and analyzer. The intensity of the light transmitted by the analyzer varies with theta according to I equals I naught cos square theta, where I naught is the intensity of the light entering the analyzer.
Polarization by scattering. Consider an unpolarized light traveling along the y-axis strikes a gas atom at A. The electrons in the atom are set into oscillation in the xz plane by the oscillating E field of the incident wave. The radiation reaching O would come entirely from the dipole at A oscillating in the z direction and would be linearly polarized in the z direction. The transmitted radiation along y-axis is unpolarized because both dipoles can radiate equally well in the y direction. Sunlight scattered off atoms or molecules in the atmosphere of the Earth may also be polarized. If the atmosphere were not there, the sky would appear black except in the direction of the sun. Polarization by reflection. When light falls on the interface between two transparent media, it is partially reflected and partially refracted. The amount of light reflected or refracted depends on the polarization of the light relative to the interface. Consider an unpolarized light striking the interface between medium 1 and medium 2. At one particular angle, no light with polarization in the plane of incidence is reflected. All the reflected light is linearly polarized perpendicular to the plane of incidence. This angle of incidence is called the polarizing angle. Tan IP is equal to n, where n is the refractive index of the medium on which the light is incident. This equation is known as Brewster's law. Polarization by refraction. When ordinary light is incident on a glass plate at polarizing angle, the reflected light is plane polarized while the refracted component is partially polarized. Now, if this refracted beam is made to strike another glass plate at the polarizing angle, the same thing will be repeated at both the surfaces of glass plate. If the process is repeated using a number of parallel faced glass plates and light is incident on it at polarizing angle, then the beam emerging after refraction through these large number of plates will have almost all vibrations lying in the plane of incidence. The transmitted beam is thus plane polarized with vibrations in the plane of incidence. Did you know? Diffraction grating is an optical component with a regular pattern which splits light into several beams traveling in different directions. One consequence of diffraction is that sound from a loudspeaker will spread out rather than just going straight ahead. Sunglasses with polarizing films on them are used extensively while fishing and boating. These sunglasses are designed in such a way that one can look right through water. Reflection of waves off seawells or other barriers can cause an interference pattern called a standing wave. In standing waves, crests do not move laterally. Summary. Let us summarize what we have learnt. Diffraction of light is the phenomena of bending of light waves around the edges of an obstacle or an aperture of size comparable to the wavelength of the incident light waves. A distinct diffraction pattern is possible only if the slit is narrow. If the slit is made sufficiently large, then the secondary maxima will not be visible. The ability of an optical instrument to produce separate images of two objects very close to each other is called resolving power. The resolving power of a lens is its ability to resolve 2 points that are close to each other. Polarization of light is the phenomena of restricting the vibrations of light in a particular plane. Malu's law states that when completely plane polarized light is incident on the analyzer, the intensity of the light transmitted by the analyzer is directly proportional to the square of the cosines of angles between the transmission axis of the analyzer and the polarizer. When light falls on the interface between two transparent media, it is partially reflected and partially refracted.
तो मेरे प्यारे दोस्तों, ये था वेव ऑप्टिक्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट।